Good afternoon. We are in the third day of the CFD short course, and I hope you have enjoyed it. And please do feel free to ask me any questions, either through email or during this time. So today's lecture concerns the pressure projection and the simple algorithm. And I will add to that the adaptive grid refinement and the meshless methods, which are becoming very popular and are very useful in modern practice. So for purpose of illustration, let's start with the two-dimensional steady state equation. The same thing generalizes to the three dimensions. And you are familiar with the continuity and momentum equations. Here they are. There is the convective terms for the U momentum, the diffusive terms or the friction terms, the pressure gradient, right? And similarly for the V velocity direction, the Y direction velocity, and this is the equation of continuity. Very simple. I've ignored other sources and things of that nature. Now, let's illustrate the problem by starting with a Cartesian uniform grid, just to make things simple. So if we do that, the pressure gradient is basically integral of pressure gradient. Don't forget, we're going to integrate. We're using always the Gauss theorem and always the integral method, not the Taylor series. So this will lead to P pressure at this phase minus pressure at this phase. That's the gradient, right? So the pressure at this phase can be written as, from central differencing, as PE plus PP, and then PW plus PP. So we get the net effect is this pressure and this pressure. And the inverse sign is here because of the minus in the dpdx. So interesting thing to notice is that the pressure, the center point, P, this point, is missing from this value, right? So when I do the gradient, when I do the integral over this control volume, this pressure is missing. Only this and this pressure one, right? Okay. This is physically very disturbing, right? For example, let's say I start injecting fluid into this cell, a lot of fluid. So where do you expect it to go? It should flow out of these surfaces, right? But this equation says, hey, the flow is going to stay zero, right? And similar thing would happen here. The flow would be zero, right? So similarly, if I lower the thing, the same thing, the flow should come in. It doesn't. This pressure has no role in this realization. Well, that's obviously not a good realization. So we need to do something about it. Now, to illustrate the point further, let's take this kind of pressure distribution, 10, 50, 10, 50, 10, 50, and the value at the interface is 30 for all of them, right? So if I have 6 tanks connected at this pressure, do you really think there'll be no flow? Actually, there'll be flow till all the tanks come back to a pressure of 30. That's what we expect, right? That's not what the equation says, so that's not acceptable. So let's look at the continuity equation. What happens there? Similarly, I take du dx, and I get this value minus this value. I take the central differences here, and I get these two quantities. They add up to this quantity. What does that say? That says this pressure velocity has no role in it. The velocity at the interface is basically this is equal to this. Okay, sorry, W is equal to this, right? So this P is eliminated from the velocity also, similar to the pressure one, right? So same thing happened in the Y component, right? This problem is called the problem of aliasing. It's essentially solving on a 2 delta X grid, because you see the middle point is eliminated from all the equations, right? And it also creates oscillation and physical. It's as if the two flows at 2 different grids, delta X apart, would be overlaid on each other. That's what happens. So how do we solve this problem? There were 2 options. First was a staggered grid. Harlow was the first one who came up with this idea. And let's explore that one first. So what Harlow did was he took the value at this point and he said that for the velocity, let's build a different control volume which is centered on the velocity. This one is centered on the pressure. Okay, I'm showing this on this velocity rather than on this velocity because otherwise there'll be overlap, right? So this would actually overlap. The control volume would overlap for this velocity, right? It'll half of this plus new one. But this is the control volume for V. It's offset by half from the pressure point. In the vertical direction, the same thing, it's offset by half, right? Similarly, in the third direction, it happens. So we now have here 3 grids to work with. This grid for pressure and other variables, temperature, things like that. This grid for velocity in the U direction, this grid for velocity in the Y direction. So if we consider the same integral now, okay, then what we would find is that this integral for this velocity now, the points that are pressure points are now at the edges of this velocity. So this will be simply P minus PE, right? Okay. So we are back to those points, and this is true. If you increase this pressure, flow would increase. If you decrease this pressure, flow will decrease, right? So this is much more physical. Same thing happened with the Y direction. I'm not going to worry about it. So with the staggered grid, the pressure differences between adjacent pressure points drive the flow. Okay, this is more natural for momentum fluxes than the previous co-located arrangement we had, right? Also, it's way works with the physics. So the control volumes, there are 3 or 4 control volume, 3 in 2D and 4 in 3D, 1 for pressure and all the other dependent variables, and 1 each for each of the velocity components shifted by half a delta X, half a delta Y, right? This does create a problem at the boundaries where we have like 1 control volume, which is 1.5 on one side, and then another one, which is 0.5 on the other side, but we have to solve that. So if you look at the U momentum equation now, the pressure gradient term in the U momentum is this one, right? Because the velocity is staggered, right? So it has a PP and a PE, the 2 computed points for the pressure, right? So the dP dx is now this one, right? Which is what we want, right? So it acts as the driver and the control volume. So this is good. So we do not yet have the pressure field itself, right? There's no explicit equation for pressure, okay? All we have is an extra equation for continuity because velocities are computed from momentum equations. So let's use that is what we're going to do. So remember in the Navier-Stokes equations, pressure by itself does not appear. It's not relevant, right? I could have any base pressure. It doesn't change, right? It's only the gradient of D, dP dx, dP dy, dP dz that appear in the one. For compressible flow, of course, pressure will appear through the equation of state in the density, but otherwise it doesn't appear. So what we do here is what Chorin and before him, like Harlow did, which is that we split the pressure field into a guessed pressure and a correction to the pressure that we will do. And we do the same with the velocities. We split them into true components, 2 components, a guessed value and a computed value. So, and a correction value, right? So here is the process. So the velocity guessed value, we guess some pressure, we get that guessed pressure, we compute a guessed velocity, right? This is the equation that computes the guessed velocity, right? Okay. Now the difference between the true and the guessed velocity is U prime, V prime, and P prime for the pressure, right? Okay. So the true, what we mean by true is the one that will actually satisfy the actual equation, not this guessed pressure, but the equation with the final pressure. So now if we take this equation or the guessed values and the true values, we put this in the equation, what we'll find is that this equation reduces to a coefficient, the continuity equation will reduce to a coefficient times a value, which is the difference between the guessed and the actual velocity we want. And they'll be on the right-hand side pressures, which are the P prime minus P star and P star, P nine, like that. Okay, right? Now, this is the term that will have the pressure gradient. And then there'll be term which on the right-hand side would have the difference between the guessed velocity and the actual velocity, right? Okay. So this is basically the equation, right? So we have the value at this point P related to the pressure difference, correction difference on the two sides, and then this thing, which is the divergence of the continuity equation, would appear on this side, right? So this is what it looks like. So we can write this equation that the corrected pressure velocity is this function of pressure P prime PE, and we get this one, right? So we can now further say that this is a second order term. If you do an analysis, you'll find this is a second order term compared to this one here. So we can ignore it for simplicity at this stage and just say UP prime is just directly related to the pressure prime, right? Since we're going to iterate to convergence, at convergence, U prime is 0, P prime is 0, V prime is 0. So it doesn't really matter that we drop this term, right? Because the eventual result for this U prime is 0. And this will be 0 then, and this will be 0. So this is a perfectly defensible condition. So UP prime basically becomes this, where the influence coefficient is basically the influence coefficient of velocity divided by this quantity, right? Similarly, V pressure, and therefore the correction is applied to the velocity, guessed velocity, by dE P prime PE, right? Okay, so what do we do now? What we do now is we go to the continuity equation. And in the continuity equation, we substitute for these values. And wherever there is U, we replace it with U star and P prime, right? So when we do that, again, we get an equation, which now gives an equation for pressure, where it is AP, UP prime, and all these influence coefficients for the neighboring nodes, and the divergence of the velocity field called D. Okay, it's the net divergence because we did not satisfy continuity with the approximate solution we assume. So basically, this was the process that originally was used by Harlow, but he had a transient position, so he didn't apply the correction like that. So the innovation that Potanker and Spalding came up with was to apply it to the velocity for steady state flows, okay, because Harlow's system will not work for steady state flows. So once we get the P prime, we can get the velocity corrections, and now we can correct the pressure. And if not convergent, we can keep on going. So it's what happens is we have the initial conditions or the guessed values. We solve the momentum equations. We substitute the UV in the pressure to get PP in the continuity. We get velocity corrections, and we check if this satisfies the equation, if U star a U and not, some kind of convergence check. If not, we go back and start the process. Very simple. Now, the problem with this thing is that it's on a staggered grade. It did allow us to do the deal with pressure decoupling or aliasing, and the flux vectors are where we needed them on the base of the tank, which is very normal, but there are a lot of disadvantages. Firstly, except for simple grades, staggered grades are not practically viable, okay, for complex domain. You need 4 different geometric definitions, right, in 3D. One for pressure, one for on. Can you imagine doing 4 grades and making sure they're all okay or whatever you're going to do? Secondly, when you have non-orthogonal systems, you may not know UV and the direction in non-orthogonal grades would change all the time, right? So you may not have the normal values of velocity UV and W like that. So it creates a problem when you have transformed the system, right? So then you need special extra half cell at the boundary, okay? And then the velocities of the controller limbs are obtained by linear interpolation. That's about the best option we have here, right? We could do something else, but that's much more would be much more difficult, right? So the physics shows that the velocity at any point is usually, if this pressure difference is significant, especially for incompressible flow, the velocity is very strongly related to the pressure gradient, right? So you do not do a linear interpolation of velocity unless you have no other option. You must correct it for pressure gradient if possible, right? So many modifications have been posed about this checkerboarding problem or aliasing problem for non-staggered grades, right? So the most common for the simple algorithm extension was that by Rie and Chow. And here is what they did. They said, okay, as before, we discretize the momentum equation we have, but now the pressure gradient is at the central point, okay? So this is the equation for that, and this is D is again this one. So the pressure equation becomes this, D is the divergence. So it's the same equation, okay, except somewhat the definition is different because of the co-located grade, okay? So now we need velocity at these cell faces, right? Okay. We know that if we use central differences of velocity, we'll end up with alternate grid points and the checkerboarding problem, aliasing. Okay. So how do we deal with that? So what we do is we go back to our basic math, and we know that any vector can be divided into a rotational and irrotational part. Now the velocity u is a vector, so we divide it into a rotational part by subtracting the pressure. Okay, there was a minus in the actual equation, so with a plus pressure gradient, this will be the vorticity part or the rotational part, right? Okay, so that's what we've done. We computed a u hat, which is the rotational part of the velocity, right? Okay, so now we interpolate the rotational part because we know it's not affected by the pressure gradient, right? Okay, so the rotational part is interpolated here by central differencing, just up plus ue by 2, right? Okay, the u hat. Now, if we substitute for u hat from this equation, what we get actually is that it is the velocities, actual total velocities, and then there is a pressure gradient which has been subtracted in this case, okay, because there's a minus sign in the original equation, right? So if we assume that AP and A, etc. are constant, we can say that UE is basically minus UE over A times dP dx, okay? In this equation, that's what we do, right? Okay, now, what we do is in the pressure projection method, simple is one of the pressure projection method, a pressure decoupling method. We split the velocity irrotational parts. We interpolate for u hat. Pressure dependent component is separately interpolated, and this is the different methodology. So let's look at that. So this is what we're going to do. UE is this quantity. We saw that. Now this is the pressure gradient, the two that we had. Okay, it brings in the third point in the picture here. See that? It brings the EE point in there because we are located here, right? So we're going to compute the pressure at EE point in this case. Okay, similarly, on the western one would have a WW point. So now we have 3 pressure points involved in this system. Sorry, not 3, but 5 totally, I think would occur in the through UE and UW. UW would have similar to, okay? And then there's a pressure gradient term, which is now for this one. Okay, so what we're doing, we are taking the u hat value, the u hat, and adding to that the pressure component. See, this is different because this P is for this velocity is this and this, right? So this is the part which will feel the pressure and prevent aliasing between these 2 points. Okay. So if we assume that APE is equal to APP and AP big E, then basically we can write UE in this simple relation where 4 pressures appear in each velocity, right? 1, 2, 3, 4, right? Okay, in each velocity, UE, UW. So therefore, we get this happens, the du dx, ue minus uw becomes this, du dx finally becomes this. Similarly thing we do by dv dx, we discretize the equations and we add them to the pressure, divided pressure equation, compute one. So the process is like this now. There is an extra step here, which is computing the u hat and v hat. Otherwise, the same procedure, you compute u star, v star, w star, or not compute, sorry. You have initial conditions or given conditions, intermediate values. You solve the momentum equation to get this. You compute u hat and v hat, and you put them in the continuity equation, right? And you use the continuity equation with the u hat values, and the divergence tell you what the pressure correction is. Okay, the pressure correction is no longer for the guessed velocity, it's for the pressure effect that is due to the split between the two, right? So the velocity correction then is this one, and then we check if it is converged, we go back. If not, we compute u hat and v hat again. So with that, unless you have some questions, I will go to the adaptive grid refinement with the remaining time I have. So adaptive grid refinement, AMR I'm calling it, is a modification of an existing mesh that we started with to more accurately capture features. And usually we do that, we call it adaptive because we're going to adapt to something in the flow. Okay, that's what it is. We want to capture the finer features because we may not have used a good enough grid at every point that is needed based upon the gradients of the values that exist there, right? So it is very useful when the flow and heat and mass transfer values have multiple scales. Okay, so there are some areas are smooth and some areas with small change, some places large gradients. Okay, so in the variation, the gradients is large over the flow, right? Such as in recirculating eddies, flows behind pipes, or flows in many equipment, right? So adaptive refinement says, don't waste your time refining your grid everywhere because in some places the rapid changes. Okay, so let's define the grid where the changes are. Okay, so that makes a big difference in the time that can be taken. So it allows for uniform accuracy everywhere in the domain rather than having higher errors in areas with a big gradients. So there are three kinds of refinement we can do with the grids. There is what they call the HP and R refinement. So the R refinement is the one where the number of points is kept the same. Just the grid is clustered in a particular area and coarsened away. So with the high gradients, we bring more grid points there. Where there are less gradients, we reduce them. That's what R refinement is. Now, H refinement is basically you add more points where you need them, okay? So typically, H refinement would say that subdivide it. We just usually say if there's one cell, make it two to start with, right? If it's isotropic refinement, that means that if there's a 3D problem, one cell will become 8 cells, right? Okay, is it 8? Yeah, 2, 2, 2, right? And or we could do an anisotropic refinement, say just gradients are varying in one direction, so let me just do that direction. Okay, so that's anisotropic refinement. Okay. However, especially if you do all directions isotropic, the number of elements can very rapidly become very large. As I said, one cell in 3D would become 8 cells. Okay. So P refinement is somewhat different methodology. We're saying, well, keep the number of elements the same, right? But let's add the complexity by changing to higher order basis functions. Like in finite elements, you would do that, or structural analysis, you do that just by going to higher orders and therefore perhaps introducing some other nodes for that, okay? Now in finite volume, it is equivalent to adding more faces to the polyhedrons. For example, if you have a 6-sided polyhedron, a hex, you might make it into a into a 12 or a 16 size ones, okay, which is a little more problematic, but still can be done. So usually P refinement is done in finite element methods. So how do we do the adaptive refinement? Well, we start with solving the problem accurately on a coarse mesh. And once we have a converged solution, we then look at the gradients and then refine the mesh. Okay, there are many ways to do that. Okay, so as I said, for isotropic one, we'll split in 2D to 4 cells rather than 2. Okay, now since we have an objective of getting good velocity or good temperature or good something or good pressure, we should decide what that objective is. Which one is the most indicative of the accuracy that we want? So for example, one indicator may be that let's take the absolute value of the gradient du and dy and sum them to, and 3D we get something, and we say we want that to be smaller than a certain number. That means the total variation of the gradient inside would be small, right? Over the whole of the field, right? In no field, we're trying to, that's one criteria, but there are many other criteria one could use, okay? So we keep on refining the grade automatically, okay, till the grade convergence is achieved and the finest mesh satisfies the required accuracy for the solution. Very simple method. This can be automated. We have done that in our code. Other people have done that in their codes. So actually, in the more advanced codes, you can just let the code generate the new grade and compute the new volumes and then just pick it up and run it again. So you don't have to do anything except say, do it, okay? Now here is a simple example that I'm going to show you where we have natural convection in a square enclosure. There's a hot wall, there's a cold wall, okay? So we started with just 4 points. We said, here is our grade. Basically just one node, right? Okay, we said this is our grade, right? Solve on it, okay? So the computer then went to the next level, and since we didn't know the direction, we said isotropic. So go to the next level, and we have this. We can go to next level, we have this, next level, this, and we similarly. So you see what happened here. What happened is that it kept on refining automatically, and it kept on creating larger meshes in the area. Since I believe this is adiabatic, this is adiabatic. So most of the changes are going to happen around this wall, right? The cold wall and the hot wall, that's where the gradients are, right? So you see where it got the grade to be eventually, and this will match the flow. And now we know that this flow is 1. Okay, this is very useful technique for getting a grid independent solution. Now, what are the actual solutions like? Well, here are the solutions that are shown. And because this was very faint in my system, so I thought what I'll do is I will just blacken this, the first and the last slide, to show you the difference, right? That occurred. This is a 4-point grade, and this is grade with I don't know how many points, okay, hundreds of points, right? So this is much like, if you do, this is very close to the exact solution that you would expect for this cavity, naturally buoyancy driven cavity, right? In between, you see from this, it went to this, then it split into this, then this, then this, finally, but you see somewhere around here, a pattern began to emerge by the 4th section. Actually, by this section, the pattern began to emerge, right? And you get a good solution. Now, if you look at the refinement in the temperature, what happened to the temperature? Of course, the first one just gave us this temperature, right? And the last one gave us this temperature, which is what is, if you look in the literature, this is what the temperature should be, okay? So this is very useful for complex problems. Now I'm going to move to the last part of my topic, and spending much of my time on that one, which is that of the meshless computing. And we developed a method called virtual finite volume, which I think is very promising for the future, especially when combined with the machine learning aspects that I discussed in my plenary lecture. So let's look at this one. So the essence of a meshless method is that we don't have to generate a mesh, okay? We just say there's a bunch of discrete points and we want to do some kind of a computation on those, okay? So traditional methods of the discrete meshes or finite difference, finite element, finite volume, spectral, they all need meshes. Okay, they rely on a shape function or a fixed collection of points or some kind of a, like finite element, tank and tube, whatever you call it. Okay, the meshless methods construct a shape function essentially over an arbitrary collection of points. There is no fixed connectivity among the nodes. Okay. Now, why do we need them? What is happening right now is that the CFD and also finite element tools are becoming increasingly powerful, robust. Okay. But their cost is becoming increasingly dominated by cost of grid generation. Okay. The traditional grid generation is very hard to automate. Okay. Because there are many requirements, okay, geometry, reading the geometry, making sure there are no flaws in it, and all those things happen, okay? So the time taken by grid generation is increasingly the primary bottleneck in a project. It's not unusual for grid generation to take weeks or months even, where the CFD analysis will take hours or days, okay? The second thing is that in traditional methods, the final quality of numerical solution is hostage to the quality of grids. And then it's expensive to go back and generate another grid and try a different. So the grid-based methods all suffer from grid quality methods. Okay, this is true of finite differences, elements, volume, spectral, all. Okay, if grid is not orthogonal to the faces of the control volumes or faces of the elements, then the computation and diffusion term becomes very expensive, okay, and it's prone to truncation errors. There's also that the higher order of the elements is lost when you go to these kind of higher order elements, right? And then if you use lower order, then there is a truncation error. So many of the element libraries are usually very simple: triangles, quads, hexstat, etc. So there is no robustness with these elements either. So what the meshless methods say is that, hey, let's eliminate the meshes altogether. And if not, then hide it from the user. That's what they're doing. Okay, either they are not telling you or they're not generating it. They're both methods. Okay. And then it's very easy to do adaptive refinement. Okay, it's easier to deal with problems that have singularities or they are stationary or moving singularities because can move the grid quickly. It's highly suited to deal with large deformations and moving boundaries. So, and then it's much easier to automate point generation than making sure that there are elements which pertain to certain constraints, okay, with a fixed connectivity. So there's many of these methods of the current generation. There is the smooth particle hydrodynamics, there is generalized finite difference method, least squarance variants, reproducing kernel, element-free Glerkin, extended finite element, and clouds, and all kind of things, right? We don't know yet which will become the dominant one, though I do think both SPH and least squares are used quite a bit. We have a method that is called virtual finite volumes, and I'll talk a little more in detail about that. So let's see first the applications of the meshless methods. In Deshpande and others applied the least squares method to computation of high-speed compressible flows fairly successfully with shocks and all that, okay? Bing Liam's group at Northwestern has applied RKPM to compressible flows problems, Stokes flow, acoustics, large idea, a whole group of things. We have applied R1 to actual industrial problems, okay? And there are many other applications now, and this is not complete at all. So I want to say that if you're interested in this field, there are plenty of paper, their whole conference is devoted to meshless. And so that's what you should do before you decide what you are going to do. So what's the methodology? Primary methods differ in the choice of the shape functions. Some are truly mesh-free, like SPH and GDFM require no knowledge, no background grid, okay? SPH uses shepherd functions, GDFM uses moving least square polynomials, and so that's it. Some others have a background grid for numerical quadrature of the weak form of governing equation, like SPH with a collocation that does that, generally two options, okay? the Galerkin methods, which again have a background quadrature. Okay, so that's what happens. So what happens in this one is that the domain of application, or your control, your not control, your volume for your equipment is covered by overlapping subdomains. Okay, each of which is associated with a function that is zero outside that subdomain. It's like having functions within that, which is basically like conceptually, if you think of a whole big tank filled with little volumes, then you devise function for each volume, each control volume, which is zero outside. Okay, so the functions may or may not be interpolatory, and that's why it gives you sometimes it gives you a lot of problems to impose Dirichlet boundary conditions, okay, which are fixed. So looking at this, we developed a virtual finite volume, which can use overlapping and non-overlapping values, but allows the Dirichlet boundary conditions to be imposed. Now, some specific modifications, such as those of coupled, meshless, and more traditional FEM, do allow you to do Dirichlet boundary conditions and also speed up the computations. Okay. So what I'm going to show is that how did we do the virtual finite volume. And one of the things we do that is that it preserves surface and volume relationships. And I'll talk a little more about that. That most of these meshless methods do not ensure that when you're dealing physically with your integrals, each integral eventually would be a control volume, though virtual. That the total sum of these volumes, which are used for the integral of these million equations, they all add up to the total volume of the system. Okay, many they don't. Okay. Then similarly, the surfaces that connect them do not necessarily add up to the same as the external boundary surface if you eliminate the middle surfaces. Okay. So let's see what happens. And then many of them, of course, as I said, do not enforce strict local and global integrals. Okay. So both computing time and memory are getting cheaper. Okay. So we can also use special domains, and there are some difficulties that are in imposing boundary conditions, Dirichlet boundary conditions, and they have provided the workaround. So these are some of the shortcomings that are referred to of the non-virtual finite volume methods, the meshless methods. They do not preserve the volume to surface ratio of the physical domain. Okay, the integration domain and the surface areas associated with the points at which integration is done. With that, some methods do not even have a concept of volume, right? Now, volume is a very important component in many ways because, for example, it's the volume that preserves the mass. Okay, it's the volume that preserves the heat. Okay, so we must have the total amount of volume. Let's say there is a source and there's a total physical volume, then the total source is in the computation must be equal to the total physical volume times the total source, right? So also many of these methods do not generally have a surface, or the integrals are done or the derivatives are obtained by means where there is no concept of a surface, okay? Only a functional or a particle properties, okay? So the surface processes such as friction cannot be matched directly. They must be imposed indirectly into the system, okay? So the volume is therefore also simulated in these one by indirect mathematical constructs, which such as the body force, for example, which conceptually is must be enforced in such a manner that the total body force is actually that in the physical system. So what we did with virtual finite volume was that let's assume first the two spheres, any arbitrary, any diameter, two spheres located at any point, right? Okay. So these two spheres, one is small, one is big, right? So if you connect these two spheres, their center points, they will always connect uniformly to the, they will always, sorry, not uniformly, they will always connect orthogonally, Okay, this will be orthogonal here, this will be orthogonal here, irrespective of the distance, direction, or diameter of the spheres. So this is very important. Okay, so because as I said, that the diffusion is much better to compute when you have and both convection and diffusion much better to compute when you have a normal phase that you're computing. Okay, so how do we do that? So the integration volume of sphere, the flux just change the spheres can be computed by orthogonal relations. And of course, the problem or disadvantage of using spheres is that spheres do not fill a space, right? If you put a squares in spheres in the or let's say circles in a rectangle, there's going to be holes in that, right? So the surface to volume ratio is not preserved and the volume is not preserved, right? So it doesn't matter how small I go to, I can decrease the amount of space, but I can never make it zero, and I can never preserve the surface to volume ratio I can approach. So here is what we do. So we take a bunch of distributed points, start with that, okay? And then we conceptualize this as circles, right? Okay, these are the circles that describe these points, right? Okay, so see, they don't hit the boundary yet, they're not taking, and they have these holes or they're overlapping things, right? So what do we do next? What we do next is we now think of these balloons, these spheres as balloons. Let's say they were made of some kind of a one. So if we fill this space with balloons, what happens is they're spherical balloons. What will happen is they'll form what is called a Voronoi polygons. Okay, what are Voronoi polygons? Voronoi polygons are basically polygons where any 2 points, like here between this and this, they connect through an orthogonal quantity. That's the property of the Voronoi. Here, this and this. See, these are 3 arbitrary points, right? But you see, this and this is normal, this and this is normal, this and this is normal, and this and this is, so all these relations are normal, right? Okay, now, of course, what I'm doing here is I have some points here. Why do I have them here? Because we expect boundary layer flow around this in this particular case. So I said, well, okay, here it's better to use some kind of one. Of course, we could done these also with Voronoi diagrams, but they may be, they may be odd shapes here, okay? So this is kind of a merger of the two. We end up with a tessellation like that, okay? So Voronoi fully, or the virtual finite volumes fill the arbitrary volume, okay? So virtual finite volume can sphere with 3D, but then overlap and other constraints must be satisfied to ensure volume surface ratio. They can be constructed polyhedrals. They can be constructed, they can be constructed with some atom. Now here is what happens. In 2D, you can show that you can fill any space with virtual finite volumes, with Voronois, right? The problem is, just like the tetrahedrals, when you come to 3D space, just like there is no way to fill any arbitrary 3D space with tetrahedrals, similarly, there is no way to fill a 3D space with polygons, with Voronois. But you can approach close to that, just like we do with TETs in the 3D, we can do the same thing there. So it is possible in theory to get a finite volume which gives you an arbitrary orthogonal map, right? Okay. Now, so for the arbitrary one, always fill with mixed polyhedrons, and there is no limit in the size of nature of polyhedron. So it's applied. We always use polyhedron. We can say you can have polyhedrons of 50 sides. We have used 60 sides and things like that. So one other advantage of using this arbitrary point, just like it is there with all the meshless methods, is that since you can connect one point to many points, the influence coefficient between two given points is much smaller. Okay, like I said before, if you have a 2D conduction problem, each point has a 1/4 influence on the central point. In 3D, it'll have 1/6. So let's say I do that in 10 dimensions, then it basically will reduce to a very small amount. So one particular error will not affect the solution. So your matrix would be less stiff and much more, will converge faster and would be more accurate. Okay, so this is what we must ensure. So what virtual finite volume does is that it starts like the typical point distributed meshless method. We distribute a number of arbitrary points, right? Okay, so SPH would deal differently with it. And least square would deal differently with it, but they'll form a collection of points at which gradients are computed to satisfy the equation. Okay, what we are saying is we already know that finite volumes work very well, preserve local conservation, and they have some other advantages. So why not just behind the scenes, without the user knowing, construct a grid which is finite volume, but the user only sees a point. User doesn't care that I have to build a grid. User doesn't build the grid. The grid is built by the system from those points. And many other meshless methods actually are building a grid behind, just like we are doing here with virtual finite volume. So this technique is used by others too. They just functionals are different and their way of dealing with it. Okay, so we have number of advantages. It's flexible like meshless methods. It has a better accuracy because one point is connected to many. Like finite volume methods, it conserves. It has a coordinate invariance because the one advantage of finite volume methods is they use areas, volumes, Eulerian distances, and all that. They don't depend upon X, Y, and Z. So you can change your direction of coordinates without affecting the computation of the geometry. And then finite volume has a long history and are more mature than some of these methods. So that's what the virtual finite volume is. It's a finite volume with a phase imposed on it for the user, which is a point-based phase. Okay. Here are some other solutions from that, and I'm going to finish with that. I think I'm coming close to my end, so I'll skip some of these. You have them available. So there's a random set of points. This is the flow in a pipe that we solved with these batch of points without doing any grading. This is a square cavity that we solved in the same manner. This is a backward facing step. These are my standard problems I started with these problems in my professional career. So I'll show you these. See here, we distributed a random set of points and we distributed more where we expect changes. And we can refine this now, auto refine it, use adaptive grid on this very easily. This is a random hexagon grid with a moving wall. Okay, one of the walls is moving. And this is basically extension. This is the flow coming through. And this is a three-dimensional square lid-driven cavity. Another simulation where we actually did combusted flow. This is the flow with combustion. Actually, combustion is occurring here. You see temperatures of 2000 and kind of this, right? So this is a reactive case. So also one advantage of virtual finite volumes is that it can be used as a glue. It can be used as a matching independent grid components, which is very important in complex geometries. Okay, most with the regular geometries, you have to kind of do a whole geometry together. That is sometimes almost impossible, or certainly very, very expensive. Okay, so what we can do is that with virtual finite volumes, of course, you can do it with any meshless method. You can take each segment, okay, and do the gridding for that separately. Okay, that one works this. For example, this one is done, grid is like that. This grid in the middle is simple. We just do it like that. Similarly, you can take each of these components, okay, and individually generate quick and easy grid, just distribute the points in them and do a Voronoi in them, you have a grid, right? Okay. So then all you have to do is match at the surface. And since you have the option in virtual finite volume meshless methods of introducing any number of points, you don't care if an element needs to be divided so you can talk to the element next door, right? So this way you can interchange these parts. You don't like grid here, you come back, you extract this, you don't have to do the grid for this again, you just do the grid for this part again and put it back in there, and there's a plug and play. So virtual finite volume proved very useful. They act as a glue to put these grids together. It is a very complex grid. As I said, the aircraft engine is one of the most complicated and one of the most advanced machines, and the geometry is very complex inside, and we did the gridding for that. And we even invented a swirler. See how simple the grid for the swirler is. But if we had to do it with the rest of the geometry, it will be very time expensive. Okay. So we can do all these details And I'm not going to show this one, but this is the final grid, and there's about 1,000 millimeter diameter holes here. Okay, imagine doing those in one. So whole of this grid was done by us in one day, okay, which would be practically impossible with any other method. So we just pasted these grids, got them independently. Doing a grid for one hole is very simple. It's a circular hole. Doing a grid for all these embedded in this part, forget it. So here is the flow from this generator, which matched from the other one. And then we also put in options with some simple geometry. This is a very simple geometry, and actually distributing the points, since these are repeating factors and this is just a pipe, they're just ribbons going on. We can do this grid in one go. Here are some references for you. And here is the summary. There's considerable promise. Technology is various stages of demonstration. We expect to see significant applications. As I said in my plenary lecture, I think this automatic gridding, meshless gridding combined with machine learning is going to make a big difference. Okay, so I think eventually it will displace the grid-based algorithms for complex industrial applications. Fluids are part of life and sustain life. I have thoroughly enjoyed every minute of my CFD involvement. Well, it even got me invited to CHD. Actually, it had gotten me invited to Brazil, but my luck, and I couldn't make it there, but I made it now. So it's so great to talk to all of you and see you here. There are a lot of things for you to do, and they should interest and intrigue you. Thank you.